Welcome to this explainer. Today, we're diving into something genuinely fascinating, the very foundation of how objects interact in our universe. We're going to unpack the Cambridge IGCSE Physics 0625 syllabus, and specifically, we'll be exploring the core fundamentals of forces in balance. You know, when you really stop and look around, it's pretty wild. Why doesn't a massive skyscraper just sink straight into the ground under its own massive weight? Or think about a skydiver. Why is it that after falling for a little while, they eventually just drop at a completely constant speed? Well, it all comes down to forces perfectly canceling each other out to create a state of equilibrium. It's like nature's ultimate balancing act. We are going to build your understanding of this from the ground up, using a first principles approach. By the time we're done, this physics concept won't just be something you memorize. It's going to feel incredibly intuitive. Here is our roadmap for today. First, we'll tackle the starter question. Second, we'll walk through the four-step framework. Third, we'll transition from everyday words to physics. Fourth, we'll look at real-world applications. Fifth, we'll talk about escaping the exam trap. And finally, we'll wrap up with a quick recall strategy. Let's jump right in. All right, Section 1, the starter question. Why do we even need this? I want to kick things off by posing a question directly to you. What physical effect, measurement, or prediction actually depends on understanding forces in balance? I want you to really, truly think about the physical realities around you right now. Take a massive concrete bridge, for example. It doesn't collapse under its own weight simply because the upward normal forces from its supports perfectly balance out the downward pull of gravity. Or consider a car driving at a steady speed on a highway. It maintains that exact speed because the engine's forward thrust perfectly equals the opposing forces of air resistance and friction. Recognizing these zero net force phenomena is absolutely crucial. It's your first real step. When you anchor yourself to these physical realities, you stop relying on just memorizing textbook definitions and you become far more capable of reasoning your way through complex, real-world scenarios. Moving right along to Section 2, the four-step framework, mapping the physics. So let's actually apply this framework to a physics concept and see how brilliantly it works in practice. Step 1. Identify the phenomenon. Let's use terminal velocity as our example. Step 2. State the relationship involved. In this specific case, the air resistance pushing up exactly equals the weight pulling down. Step 3. Explain the underlying physics. Now, since these opposite forces are perfectly equal, the resultant force is exactly zero. And, thanks to Newton's first law, we know that means acceleration is zero. Finally, Step 4. Connect it to an observation. This explains why our skydiver is falling at a constant, steady speed. If you can walk through these 4 linked steps for any concept, you're doing 2 things. You're demonstrating deep conceptual understanding, and you're showing practical application. And honestly, that means your foundation is rock solid. Which brings us to Section 3, everyday words to physics, making the transition. Now, this is a critical turning point in our learning journey. We all start with concrete, everyday explanations. For instance, in everyday life, we might just look at something and say, wow, that's heavy. But to really secure your understanding, you have to level up. You must transition to precise physics vocabulary, defining it instead as the gravitational force or weight acting downwards on a mass. This exactness, it matters immensely. Think about analyzing a force extension graph for stretched spring. If you understand this precise vocabulary, you realize the shape of the graph isn't just a pretty picture. The slope itself has a precise physical meaning. It literally represents the spring constant. Moving from casual, everyday observation to exact definition is exactly how you master the material. And that leads perfectly into a golden rule for dealing with fields, forces, and particles. You have to focus on cause and effect rather than isolated facts. For example, don't just blindly memorize the phrase, resultant force is zero in a vacuum. You need to understand the actual cause and the resulting effect. Because the thrust and the friction are equal and opposite, which is our cause, the effect is that the object stops accelerating and maintains a constant velocity. It's a chain reaction. Understanding the why and the how behind a physical change will always serve you better than just knowing a disconnected fact. That takes us to Section 4, real-world applications, beyond the classroom. Ideas stemming from forces in balance don't just live on a whiteboard. They are everywhere across these disciplines. In civil engineering, understanding balanced forces dictates the exact tension in the cables required to keep a heavily trafficked suspension bridge from catastrophically failing. Or look at aerospace. Calculating the precise millisecond a rocket's upward thrust exceeds its downward weight is what dictates a successful liftoff. You should always be able to name at least one real situation where balancing forces predicts an outcome. and more importantly, be able to explain exactly why the physics helps us optimize that scenario. All right, let's talk strategy in Section 5, escaping the exam trap, structuring your answer. We've all been there. You get an exam question, and there's this huge temptation to just throw a formula onto the page. For instance, just scribbling down F equals ma without actually explaining what those variables mean in the specific context of the question. Let me tell you, that disconnected approach will lose you marks every time. But there's a fix. The safest method to secure top marks completely counters those errors by using a robust four-part structure. First, explicitly define the forces acting on the object, like weight and air resistance. Second, state their relationship, clearly noting that the forces are equal and opposite. Third, explain the underlying physics by stating that the resultant force is therefore zero. And finally, apply it to the situation by concluding that the object's motion remains constant. It creates this beautiful, unbroken chain of logic that proves your reasoning is absolutely foolproof. Finally, we arrive at Section 6, the quick recall strategy, 4 prompts. So whenever you're reviewing, I want you to test yourself with these 4 simple prompts. 1. What is the core idea? 2. What changes physically? 3. What quantity or graph shows it? And 4. Where is it used? If you can answer these out loud with confidence, your foundational knowledge is entirely secure. For instance, if you are asked what graph shows forces in balance, you should be able to instantly picture a flat, horizontal line on a velocity time graph, indicating zero acceleration. It's a quick, highly effective way to guarantee your brain is ready for literally any structured question they can throw at you. To wrap up our explainer today, I want to leave you with a direct challenge. Right now, can you describe one real-life experiment and justify its link to forces in balance using a clear cause and effect chain? Try to apply the 4-step framework we just covered to something in the real world today. Thank you so much for joining me, and keep exploring the amazing physical realities all around you.